Good morning, everyone. It's a great pleasure to be here again. This is the sixth talk in the series. We're back in the US this time on the East Coast, University of Maryland, JQI, Chris Monroe's group, and Marko Cetina. He will tell us about a large ion-based quantum computer. And from what I've seen before and talked a little bit earlier, quite large. So looking forward to hear it. Marko has done his PhD at MIT, Vladan Vuletic's group, at one of the first cold atom experiments, and also on one of the early ion cavity experiments. He moved to Rudolf Grimm's group in Innsbruck to do a postdoc, and he's one of the world experts in trapping ytterbium atoms for quite a long time. So we're looking forward for the talk. As usual, please put your questions on the chat or raise your hands, and we'll take them mostly at the end, but if there's something urgent or important, we can also take it within the talk. So Marko, the floor is yours.
Thank you, Dimitris, for that introduction. It is a pleasure to be here, if virtually, and I hope that I will be able to portray well to you the large effort at Maryland to scale up computing with trapped ions. I will be presenting the effort of many people and within the University of Maryland Joint Quantum Institute. And I want especially to thank IARPA for their generous support of this effort under the LogiQ program with the goal of implementing an error-corrected logical quantum bit, for which a large system is required. So the system that I will be talking about, we like to call Eureka. It is shown here as a black box, but I don't want to keep it hidden from view. I will be opening the box and really telling you about both good things and some of the dirty laundry of the system. The box itself, however, helps for environmental insulation and passive stability of the addressing system for the qubits. This system, as I mentioned before, is the result of joint work of many people, and I especially want to emphasize our support and close collaboration with Sandia National Laboratories, who supplied the crucial ingredient of our setup, the ion trapping chip, EOSense, who have supplied an integrated lasers in a rack format, called Quanta, who are working on developing and packaging these chips from Sandia into very portable packages, similar to their work they've done in neutral atom systems. Harris, who have delivered and have enabled their individual addressing of our qubits via their 32-channel acoust-optic modulator, and Coherent, with whom we have a close collaboration to modify and improve their standard commercial product, which serves as our qubit control laser. And of course, I want to especially thank the funders for the generous support that has made this possible. This has been a long journey that has now blossomed into a large effort. You're probably aware of IonQ, whose systems are actually based on this platform that I will be presenting. I want also to emphasize that during these shutdowns, we have remained fully operational, and this is, and not only that, but I would say we have been more productive than ever before. This is owing to the nature of the system, where it is remotely controlled. So in order to achieve the high stability that is required in order to control a multi-qubit system, you pretty much have to provide all the necessary knobs that can be tweaked and be able to operate these knobs, the relevant ones, remotely. The less relevant ones, like laser locks, you just make robust. So if you've made such a system, you're well on your way to being remote, and we have been operating remotely since about last year, end of last year. And we have just continued basically this working from home and going into the lab once a week to reboot a computer or exchange a gas cylinder or something like that. The bigger challenge for us right now, and I would say for everybody running large quantum systems, is really the automation. So being able to have the system be self-calibrating and self-running and self-supervising. And this, in our mind, we've discovered is a much bigger challenge. It is largely a software challenge and also one that can be done from home, but a difficult and a necessary one that we're very much struggling with at the moment in order to be able to perform long depth circuits with high fidelities, low unitary errors on many ions. I want to thank all the members of the team, both present, shown here during the shutdown, everybody working from home, and previous that I will show later. As I mentioned before, at the heart of our system is a microfabricated trap made by Sandia National Laboratories. This is about 1 centimeter on the side, and this is the result of, I would say, a decade of the development of such traps by the ion trapping community. I remember the beginnings of that and just how much people struggled to trap even a single ion in these traps, and certainly a chain for a few minutes. The fact that we can have a chain of about 30 ytterbium plus ions trapped in such a trap now for 45 minutes regularly is really a testament to the great progress that these traps have made. As I mentioned before, the addressing of these qubits is accomplished using this 32-channel acoustoptic modulator shown here. It looks just like your standard AOM, but with 32 cables coming off of it. And this allows us to turn individually addressed beams on each of the ions and manipulate them in a targeted fashion. As a further example of the control, in order to start working with our ions, we load one ion at a time. In this loading zone, there's a little hole in this trap, and we send a flux of ytterbium atoms, and we photoionize it, and we load individual ytterbium ions in this zone. Shown here, sped up by a factor of several, is the process of loading, where we take these ions that are loaded, we shuttle them a whole millimeter using voltages through a junction, and then we use that to build up a chain. So here is a picture of the building up of this chain, sped up by, as I was saying, about a factor of 3. And again, I remember 10 years ago, the great achievement in Michigan, while Chris was there, was being able to get an ion just around the corner. So now every single ion that we work with has rounded this corner and traveled a millimeter, and this all works actually in an automated fashion. If you want 15 ions, you can click and you can get 15 ions. Of course, in order to build a good quantum computer with many qubits, it is crucial that you have a good qubit. And the system that we're working with indeed has an excellent qubit based on atomic physics, which is the first order magnetic field insensitive, F equals 0, F equal 1, M F equals 0 transition, hyperfine transition in ytterbium-171. This transition, as you probably well know, can be manipulated using microwaves, shown here. We apply a microwave pulse of variable duration, and we transfer the qubit from 0, 0, where it's been optically pumped, into 1, 0. By doing that, we can, as other groups, measure the T2 time, here done using multiple echo sequence. We show that in our system, in the black box that I'm showing, we have T2 times of several seconds, probably partially limited by the quality of our microwave oscillator. And T2 times of in excess of 10 minutes have been published by Ki-Hwan Kim's group, Tsinghua, and the more recent work there has achieved more than half an hour. So that gives us a very solid foundation to do all our quantum computing on, and some of the results I will be presenting later will be error correction And I want to point out in that context that the challenge we have is not with the qubits, whose errors we need to control, but almost exclusively the errors that are caused by the control, by the gates that we perform on the qubits. In order to detect the state of our qubits, we, as you also are probably familiar with it, we use resonance fluorescence. So we shine near resonant 369 light on the D1 line of ytterbium plus at 369 nanometers, and owing to the pretty large hyperfine splitting in the ground state, this laser is only resonant with f equal 1 to f equal 0 transition. And so if the qubit is in the f equal 1 state that we call up, it will scatter light, and we will collect photons whose histogram you can see here. Whereas if it's in the f equal 0 state, it will remain dark, and we will see very few counts. The off-resonant scattering from the other hyperfine states limits the detection fidelity of this scheme to about 99.8%. However, more recent work like at UCLA has shown that with optical pumping, albeit slowly into other states, much higher fidelities can be reached. So in order to perform this detection, we need to do it for each of the individual ions in our chain. And we do this by coupling the light of each of the ions with high numerical aperture to collect as many photons as we can before these bad pumping events into one of 32 multimode fibers. And I want to emphasize that because these are multimode fibers, this is pretty easy. Most of the light, 70% of the light makes it in. And then we couple these individual fibers to individual PMTs. And to check how well this works, we here have an example experiment where we have 3 ions that we move using an electric field past 3 detectors. And we record the counts on each of these 3 detectors. And as we do that, we can obtain the photon collection crosstalk as well on the nearest neighbor channels and the nearest neighbor channels. And after thresholding, this corresponds to state detection error that is less than 0.5% crosstalk on the neighbors and 0.02% crosstalk on the next nearest neighbors. And some of this is limited by aberrations, which we can readily improve. Now, in order to manipulate these qubits, we need to do it in a qubit-specific way. So we need to do something akin to our microwave transfer, but within a targeted fashion for each of the qubits. And we do this using a Raman process driven by 355 nanometer laser. And this laser is pulsed. So that means that the Raman beat note, which drives the coupling, so the Raman Hamiltonian can be thought of as a sigma x Hamiltonian that flips the qubit state, proportional to the intensity of the laser, and an additional frequency shift that is supplied due to any frequency and phase difference between these 2 tones that are applied between the 2 legs of the Raman process. So we can think of this Hamiltonian as a optically addressed radio frequency beam, because all the time dependence here is in the radio frequency domain. And meanwhile, we have the optical addressing of a laser. Furthermore, by using a pulsed laser, this intensity as a function of time is broadband. And so it spans the 12.6 gigahertz hyperfine splitting. And this allows us to directly be resonant with one of these intensity comb teeth and be able to transfer the qubit using only this one laser. We don't need multiple phase lock lasers. We have only a single oscillator. And furthermore, because only the intensity of that oscillator matters, any phase noise of the laser itself drops out. So we really think of this as a kind of optically steerable radio frequency source. Now, one might say that if you have all these comb lines, if you have a pulsed laser, you may have some spurious problems like Stark shifts. And we have investigated this. We have investigated the additional Stark shifts, the 4-photon Stark shifts that arise from this Raman process. And what we've shown is that by controlling the repetition rate of this laser, which we can do thanks to a collaboration with Coherent, to modify their laser to move one of the mirrors inside, we can null the 4-photon stark shift that arises from all the off-resonant lines. So in this way, the deleterious effects, I would say all the deleterious effects of the pulsed laser are removed, and we are left with, exactly as I was saying, almost perfect qubit addressing system that acts pretty much like perfectly phase-locked continuous wave lasers. Now, as I mentioned before, we need to actually do the optical addressing. This is achieved using the Harris 32-channel acousto-optic modulator, which modulates one of the two beams in the Raman scheme. This would be this beam here that we send through an opening in our trap. So our trap is mounted upside down in space. It has a slot in the middle of it. The ions are about 70 microns from the surface. And these individually focused beams shine through this slot. And the other leg of the Raman process is we call it a global beam that is kind of like a floodlight that illuminates all the ions in the chain. So the interference between these two beams drives the Raman processes that manipulate the qubits in this fashion that I'm showing here. Using this scheme, we performed single qubit gates, and in order to suppress intensity noise and also suppress crosstalk between the neighboring channels, we use shaped SK1 pulses, and using these pulses in a randomized benchmarking sequence, we show gate errors of less than 0.1% per gate in both single ions and 15 ion chains that are individually addressed. Now, of course, in order to do quantum computing, we need to be able to perform 2-qubit gates, to perform entangling operations. And you probably know that ions can do this quite well and have been doing it for a long time, and that the way to do that involves the motion of the ions. So information will be exchanged via the joint motion of the ions. In our case, we use the radial modes of motion of the chain, which have a number of technical advantages, one of which is they're much less susceptible to heating and stray fields acting on the ions, and also they have a narrower bandwidth, which eases their addressing and manipulation by the lasers. So I'm showing here a radial mode spectrum after sideband cooling of our usual 15 ion chain that we work with. The blue lines are the blue sidebands where the Raman beat note drives carrier frequency plus one radial motional frequency. So the frequency of the Raman beat note is qubit frequency plus various frequencies that I'm scanning here on the x-axis. And the red, where the laser frequency is the qubit frequency minus delta. And we see high asymmetry between the red and the blue sidebands, indicating that our sideband cooling is working well. What I want to emphasize is that in these chains, all the heating that you see is centered in these radial modes, for which all the ions kind of move together. The zigzaggy modes, that are most of them, are not heated. And that is because the electric fields that cause heating are fairly correlated in space. So they can drive these modes, but not so much these modes, which means that if you work with these modes here, you do not experience basically heating of these modes during your gates. So the mode heating has a negligible effect on the gates, direct effect. So this is a very nice advantage of using these higher order modes that we do for using our gates. So now in order to implement our gate, as some of you may know, we drive two tones at the same time. So we shine an individually addressed beam onto a specific ion, and we apply together a blue sideband, so Raman tone at qubit frequency plus delta, and a red sideband at qubit frequency minus delta. If you go through the math, you can see that this Hamiltonian is equivalent to a state-dependent force. So because the Raman process involves absorption and emission of photons in different beams, it also pushes the ion. if you have this pushing on both the blue sideband and the red sideband at the same time, what you end up with is a force that depends on the state of the qubit in the x basis, not the z basis, but the x basis. And now, if you do this on two ions at the same time, both of which are individually addressed in the radial direction, you will have a force that depends on the sum of the two forces in the two ions. So depending on the states of the qubits, so in this case, down-down, the various modes that you drive will execute trajectories in phase space. Now, the trick that we use is that we shape the amplitude of this laser beam as suggested in 2006 by Lumin Duan et al. In order to ensure that all of these modes close. So for all of these modes, no matter where we start in phase space, we end up back. So we disentangle the spin from the motion of these modes and come back where we started. So we do not leave information behind at the end of this operation. So the only effect that this operation then will have will be a phase proportional to the area in phase space, some of the areas in phase space enclosed by all these modes. Now, if we do it, and I want to emphasize that one may think that as the number of ions grows, the difficulty of shaping these pulses also increases and that it becomes very difficult. However, we have found that it is actually quite a relatively easy to do polynomial problem. So while the gates do slow down some, this is not at present a really big obstacle for working with long chains. The more important obstacle I will be discussing in a few minutes. So this pulse shaping really works great, as you will see, on chains of 25 ions or potentially more. So if the qubits start in a different combination of spins, then the total force is different, and the areas that are enclosed in phase space will also be different. So if you put this together, you can make a truth table in the x basis, which corresponds to a phase gate in the x basis. If you switch to the z basis, it will look like this, which corresponds to an XX entangling gate in the z basis. And this is the well-known Molmer-Sorensen gate, as suggested by Molmer-Sorensen and Milburn and Solano in around 2000. So we have tried this out on a chain of 15 ions, here ions 2 and 3. And we map out the fidelity of this gate in the usual way that we apply the gate starting with both qubits in the 0, 0 state, and we should end up with the superposition of 0, 0 and 1, 1. And we check that by a direct measurement here. So we apply the gate and check, and we see that indeed most of the population is in the 0, 0, 1, 1 subspace. But of course, in order to see that we have a correct gate, we also need to check for coherence between 0, 0 and 1, 1, which we do by applying rotations with around an axis, a variable axis in the xy plane. And by putting together the contrast of the parity oscillations in this way and the subspace population in the well-known way, analogous to the first demonstration of a two-qubit entanglement with ions, we obtain a sample fidelity here of 97%. More recently, we easily achieve gates with fidelities above 99% on 15 ion chains. But if we wait before this gate, if we simply spend some time in the dark and then we apply this gate, we see that as a function of wait time, of just letting these ions sit there and not doing anything to them, the fidelity decreases. The sum of the populations, P00 plus P11, stays quite high. However, the fidelity, the contrast, the coherence drops. So can we explain this? We've been able recently to explain this effect by a process that is encountered also in other quantum computing platforms with individual addressing, such as Rydberg systems, where the culprit is the thermal motion of the ions relative to the individual addressing beam. So what happens is that due to the thermal motion, the ion, even if the gates are rather slow compared to the thermal motion, it will see an average Rabi frequency. If the ion kind of fuzzes out and moves more back and forth, this average Rabi frequency that it sees will decrease proportional to the energy of the motion. But, of course, the energy is Boltzmann distributed, which means that the average Rabi frequency that you have, whether in single-qubit or two-qubit gates, is subject to thermal noise due to the thermal spread in energy. And this we can characterize by unitless parameter theta, which is basically the simple unitless parameter you can make from the curvature of this laser beam that is doing the addressing. And so this is generic for any scheme that involves focused addressing of qubits. And we've investigated this by trapping a single ion, either in a tight trap, so 710 kilohertz axial frequency, or in a very loose axial trap, where for us the loose direction is axial for the motion of the ions. And we, in a tight trap, we see minimal decoherence when we do slow Rabi oscillations, whereas if we relax axially the trap, we see striking decay in the amplitude of the Rabi oscillations, whose phase and whose detailed phase and amplitude behavior agree very well with this model that I presented in the previous slide, and do not agree with simple T2 damping. So this hints that we do have a good handle on what is going on. Now, what happens in a chain of ions? Well, you have the same process where each of the ions is experiencing this type of fuzzing. Again, if you do some addressing, the derivative term in your Rabi frequency, if the gate is relatively slow, will disappear, and you will be left with effects of the curvature. But you may think, but in a chain, you have many modes, and if you Doppler cool to a certain temperature, your thermal energy will be spread across all these modes equally. So you will actually have only a small fraction of the thermal motion being the low frequency modes that move a lot. All the other modes are much higher frequency and correspond to a much smaller motion. However, if you remember before me talking about the heating of the ion chains, because the electric fields that are causing the heating of these ions with time in traps are correlated in space, it is the low order modes that are heating. And which means that if you wait tens of milliseconds, the dominant mode will actually have all the ions moving together at the lowest axial frequency. So the relevant mode, quote unquote, is analogous to actually the case of a single ion at the same axial frequency as the lowest frequency of the chain. And if you go through the math for that, you see that this error, and you're aware that this lowest mode frequency in chains that have a near equispacing scales roughly like 1 over the number of ions. And if you take a typical spectral behavior of this, of the noise density of the electric field as 1 over the omega, you end up with a very high steep power of this heating process as function of the number of ions, so n to the 6th. And this looks really scary. So when I talked about large quantum systems, this n to the 6th seems like a big obstacle. So, well, first, is it true? Unfortunately, it is. Here we show the data as before on 15 ions, both after the fidelity after 1 entangling gate on 15 ions, and the fidelity after 3 entangling gates on 15 ions. And we obtained very good agreement with this theory, which actually uses this heating that was measured using Rabi oscillations, and that agrees with what we expect for our trap. So the expected heating rate, the expected noisy electric fields in our trap, due to various surface processes, explain actually the observed behavior in 15 ions. And we have observed similar behavior on 25 ions, where I want to highlight that this is the largest at present individually addressable and fully controllable with arbitrary pairwise interactions quantum computing platform that we have. And this platform is very clearly limited by this heating process. So what can we do about it? Well, the main solution's been suggested in the ion trapping community since 2000, and before, which is to do sympathetic cooling, analogous to neutral atoms, where one species, colored here in cyan, would be cooled using some cooling scheme, while and this cooling could be interspersed with operating gates on your qubits. So in this way, you could really keep this axial motion in check. This is especially probably easy because you really mainly need to cool this axial mode. In the context of our system, we would like to suggest a particular cooling scheme, which has the very nice property that it uses all ytterbium, but avoids the crosstalk between the cooling ions and the qubit ions. And this is accomplished by using narrow line cooling. So we suggest to do the sideband step, to do sideband cooling on the 435.5 nanometer electric quadrupole line, and perform the repumping, the reset operation of sideband cooling with the 935 nanometer repump, which has already been demonstrating in ytterbium 171 by the Sandia group. And if this same scheme is applied to 172 sympathetic coolants, then we anticipate very small errors corresponding to several seconds between the times when the rescattered 297 nanometer photons from these sympathetic coolant ions disturb our 171 ytterbium ions. And this would be the dominant crosstalk scheme. So one application of the system that we have explored in a fair bit of detail that is in line with our funders is to do error correction in a quantum computer. And so to explain what we're trying to do, I would like to draw the analogy to classical error correction. And in this simple case, we could try to protect a single bit against errors by encoding the state of a single bit in the state of 3 bits. And instead of looking at the state of 1 bit, we consider the state of the logical bit to be the joint parity of the 3 bits. So the way we can protect, against errors in this setup is if any of the 3 classical bits experiences an error, like a bit flip, we can compare the signs of the various pairs, and by doing that, identify which bit flipped. So in order to perform a quantum version of similar error correcting code, because their quantum errors have more degrees of freedom than classical errors, we generically need more qubits. So the code I will be talking about is the Bacon-Shor 913 code, which implements 1 logical qubit with 9 physical qubits using a distance 3 code. And the check operations here are highlighted with these rectangles, and they correspond to the joint parity in either the Z basis in the case of the brown plaquettes, or in the X basis in the case of the blue plaquettes of the 6 tuples of the qubits. And the code that we one of the qubit states will look the states that correspond to the encoded qubit will look something like that. So they're entangled states, but as before, as with the classical qubit, with the fixed joint parity. So again, it will be the total parity of the whole system that will set our logical zeros and ones. And in more detail, this Bacon-Shor 913 code has a number of nice properties, which is the reason we selected it. And it is especially relevant, we believe, in collaboration with Ken Brown's group at Duke, that this code is relevant to scaling up quantum computers based on it, because it allows transversal operations, that is to say, between logical qubits that are performed only pairwise. So if you want to do a operation between 2 logical qubits of this type, either an XX operation or you want to do a single qubit operation on on this encoded qubit, you only need to operate on the individual qubits 1, 2, 3, 4, or on the pairs 1, 1 prime, 2, 2 prime, and so on. So it has a ready generalization to scaling up. Furthermore, very importantly, all of encoding, readout of these stabilizers, of these check measurements, and logical operations can actually be performed fault-tolerantly. And some of these fault-tolerant steps we will demonstrate in the next few slides. We implement this code on our usual 15-ion chain. We use 9 of the ions as data qubits and 4 of the ions shown here as the ancillas, to which we will map, as shown, the joint parity of the plaquettes. So the parity of the blue plaquette, the appropriate basis, will get mapped to 12. The parity of the yellow plaquette will get mapped to 11. So the first step in operating this logical qubit is we need to encode its states. And here is a sample encoder for preparing the logical 0 and 1 states. So here is a sample circuit. And if you actually look at this state, after preparation, you look at the various populations, it corresponds to the various combinations of states with the same parity. So even parity in the case of logical 0 and odd parity in the case of logical 1. Analogously, we can perform preparation of the plus and minus logical states, and these actually correspond to triplets of GHZ states. So a GHZ state along each column here is our preparation. And this block behavior, this block nature of the encoding is intimately related with the fault-tolerant properties of this code. So in order to, we then check the quality of our preparation, and I am showing that here for all of 0, 1, plus, and minus. And we can look at the joint parity, which will tell us the logical qubit state of the raw, shown here of the raw system. And we see that we have errors that between 10 and 20%, higher errors for the plus and minus states that we ascribe to the higher phase sensitivity of these states to various types of phase noise. But again, this is an error correcting code, and even though here we do not use any ancilla, we still have access to these stabilizers, to the Z1 and Z2, because we measure in the Z basis. So we can use the values of the Z1 and Z2 stabilizers to try either to error correct using this scheme, or to just use it as error detection, just to check whether an error occurred. We see a dramatic reduction in error after correction, indicating that most of our errors are weight 1, and error correction works really nicely. And if we use it as error detection, we have errors that are at the level of the statistics of about 10,000 shots that we perform in these experiments. So this is a very nice demonstration of a fault-tolerant preparation of a full logical qubit with the entirety of the code being executed to encode. So having achieved the encoder of the logical qubit, we now proceed to perform logical operations, which, as I said before, have this nice transversal property. The fault-tolerant transversal operations can be performed as follows. They consist of individual rotations on each of the qubits and a relabeling. So we perform this block here with a variable number of times. So we try to Rabi flop, if you will, the fault-tolerantly Rabi flop the logical qubit. And the data is shown here. So we prepare it. Again, the red line corresponds to the raw data with no correction or detection being applied. We see a decay indeed in contrast compared to the physical qubit. But after error correction applied in an analogous way, the fidelity of our logical qubit throughout this logical Rabi flop actually exceeds the about 99% fidelity of the Rabi oscillations of a physical qubit, albeit in the physical qubit, the 99% is limited by the state preparation and measurement error, which is suppressed owing to the redundancy of this code. And if we perform it using error, with error detection, again, with the full statistics of about 50,000 measurements, our errors are consistent with 0. So this works very, very well. And this is, again, in collaboration with Ken Brown's group. In addition to contrast this fault-tolerant rotation, which can only be performed discretely, right? Only these pi/2s can be performed in a fault-tolerant fashion. They're highlighted here in blue. Here is the discrete pi/2s applied to all the qubits, followed by the permutation. We can try to apply a continuous rotation to the qubit. But owing to the Easton-Neal theorem, there is no quantum error correcting code that can transversally implement continuous operations and hence implement a universal gate set. So we cannot do this fault tolerantly. And indeed, when we design a circuit that to do this continuous rotation while staying within the code subspace, which then involves entangling operations, we observe a decrease in the amplitude of the Rabi oscillations, and we also note that in this continuous rotation, the error correction does not help us very much, which we ascribe to the fact that we have a number of 2-qubit gates in order to implement this continuous rotation, and these 2-qubit gates involve weight 2 errors, which are not well corrected at all by this correction scheme. In contrast to the weight 1 errors that were happening in the fault-tolerant rotation above. So this shows, again, the power of fault tolerance in not only now in preparation, but also in the operation of your logical qubit. And again, this is with very close collaboration with Ken Brown and his student Debopriyo at Duke. And the work led at UMD by Laird Egan as the senior grad student. So having demonstrated the encoding and the operation of logical gates, the next step that we showed is we demonstrated a part of the stabilizer measurement. So we map the joint X parity of these qubits of a quarter of our qubits, so quarter of the full stabilizer to one of the Ancilla. And here is a sample circuit to do this and the data. So the various rainbow colors are the 6 qubits, which live in one of these plaquettes that are mapped to the Ancilla, and the black is the Ancilla. And we show here the population, so the state of both the registers and of the stabilizer after the measurement. And we can do this in a sample state, and then we can do it for all the 64 different states of the 6 initial data qubits. And the errors that we see on the both on the Ancilla and on the physical qubits agree with what we expect from the fidelity of our individual entangling gates. And also the error, of course, on the Ancilla is larger because 6 XX gates act on the same Ancilla, whereas only 1 gate acts on each data qubit. And we want to emphasize that we have very good separation between the Ancilla being in one state and Ancilla being in the other. So we anticipate being able to discriminate fairly well between whether there is an error corresponding to one state of the Ancilla where there isn't an error, and hence use this information in the future to perform error correction.
Marko, if I can interrupt,
yes.
There is a question. Ben Olsen, you can unmute your mic and ask the question. There's a question by Ben Olsen. I can read it, but
sure.
Ben, go ahead, please.
I guess this is for the first half of your talk. Sorry, the question came up so late, but you mentioned loading 171 and 172 ions in the same chain.
Yes.
Is that pretty straightforward to do experimentally? Can you, like you said before, you can just type in, I want 15 ions. Now can you type in, okay, 3 172, then a 171, and you sort of sequence it that way deterministically?
While we haven't done that yet, I anticipate that to zeroth order it is very easy because our photoionization is very isotope selective and our loading is very reliably one at a time due to some charge blockading effects in the trap. The problem is that while you're loading, which takes about 2 to 3 minutes, at the very least your oven degrades the vacuum, and collisions with background gas atoms will randomly reorder the chain. So you can load the correct numbers, but the ordering that you end up in is going to be random. And furthermore, as you run your circuits, these collisions will continue happening, albeit at a lower rate, because the vacuum has improved since you turned the oven off or shuttered it, but still they will reorder. And we've measured this, and in our system on 15 ions, they reorder once every 2 to 3 minutes. So, whereas our loading process with our oven takes about 2 minutes, dominated by the warm-up time. So what we're doing is implementing an algorithm to sort the card deck. So we anticipate being able to do that in a few seconds to controllably reshuffle the ions and get them into the right positions. And the key instability there, the key challenge is to be able to split ion chains repeatedly and isolate pairs and then perform transpositions of pairs. In these splits, we believe we'll be able to do very, very reliably thanks to very good electric field control in the axial direction. So the qubit performance I was showing, the gate performance I was showing so far is actually quite a bit in excess in terms of what electric fields or axial control of the electric fields is concerned compared to what is needed for this reordering. So we are quite, while it's a bit of a Rube Goldberg machine, we're working hard on this, and we hope by the autumn to have this deck reshuffling working. And this should really open the door to both the sympathetic cooling to give us high gate depth with many ions, and also, as I want to highlight at the last slides, to actually implement the full logical qubit. Because the same rescattering problem from one ions to others that is encountered by sympathetic cooling is encountered if you want to read out your Ancilla, which you need to do in order to then determine what you need to do to fix your errors. So our strategy is to split the chain into subchains and read out one of these subchains. To do these splits and merges, you heat up when doing that, and you have to recool. So it is the addition of the sympathetic coolants that will enable the split merge and the full operation of the logical qubit. So these are very synergistic for us.
So is it easy to detect like when the ions have spontaneously reordered?
Yes, thank you for that. You can certainly, if you shine 369 light for one isotope for Doppler cooling, the other one will appear basically dark. So your dark PMT channels would indicate that those are the other ions. But since in this reordering algorithm, you need to do this with very high reliability, what we really will be doing is alternating between two different colors of the 369 light and checking which ones are one isotope and which ones are the other. And then that will give us, and remember, we have these individual channels, so we get a binary string that tells us you have 171 in these positions, you have 172 in those positions, there you go.
Thanks.
Yeah, and we in this Ancilla readout, we've demonstrated already that if we separate our ions by about I cannot see it by 1 millimeter, which are trap supports, we have truly negligible errors caused by a detection pulse. So as soon as we can do this shuttling during our coherent sequence, we should be in good position to do these operations. I'm running out of time, so I won't discuss much. There's relations between the error correcting codes and quantum simulations, and we're very much interested in the quantum simulation direction as well, in what can be done with this mostly digital system. Maybe an intuitive guideline for QSIM with this is that this system is very good at doing gates, so compressing your simulation to do entangling operations with large angles, kind of QAOA style, is desirable. So if you trotterize, you'd prefer larger trotter steps. Because remember, you have this wall clock, basically. If you do gates for a long time, things are heating up, at least in the current state of the system. So it's a bit QAOA-ish quantum simulation platform. And with that, I would like to thank the whole Monroe group, and especially the people who are present, highlighted in blue, and past, highlighted here in black, who have participated, built up, and greatly contributed to this terrific system that we have. Thank you.
Thank you, Marko. Very nice talk. Are there any more questions from the audience? Just raise your hands or unmute your mic. I think some will be taken in the follow-up session, the closed session with some of the experts. I have one general question. So, what's the largest kind of number of ions that have been entangled there and in the lab, basically? And in terms of application, the second part is, you mentioned QA towards the end.
Yes.
Are there any plans, or have there been any works in that direction, running any, it's very popular these days to talk about running chemistry, running QAOA, optimization, this and that. Are you guys interested in that direction? Or?
We are, and the work, there has been work on the quantum simulation platforms, where, as you well know, there are these easing interactions across all the ions in other of Chris's experiments. And there have been QAOA simulations, things done on a smaller system by Norbert Linke. And there have been, exactly in the vein of quantum chemistry, you're probably familiar with, at IonQ, with similar systems. What they weren't QAOA though; they were just they were chemistry. There wasn't feedback.
I see.
Classical quantum feedback.
So there was no.
Norbert's had feedback, classical quantum, and what you find is that. In these things, compiling, so thinking hard about kind of pre-compiling, like in chemistry, and independently computing various terms in the Hamiltonian, is very important for these systems. So the tight theory collaboration that really optimizes what your optimizer for the platform is, we've found, and especially the IonQ work found, is very important.
Okay.
So basically, we are happy to run whatever, but at the same time, we should have a good discussion. On,
yes. We're aware of a few. I mean, we can talk more later, but just briefly before we close, there have been works on quantum simulation of time crystals. We've seen. I think some QAOA, as you mentioned as well. I guess the group has different sections. I guess different experiments are running in parallel. You mentioned a little bit on the quantum simulation. You could tell us on the last slide what's exactly the quantum simulation direction there, the one before last. Yeah, what is this model?
So the kind of the big picture view here is that the easing simulations that have been done with ion chains so far have involved XX interactions.
Yes.
Only. And many interesting models involve more complex interactions like XX plus YY plus ZZ in various Heisenberg models. And we can readily implement these by trotterizing.
Oh.
Where XX and YY are actually entirely native for us. And ZZ can be implemented by rotating by pi over 2, doing XX, and then rotating back. As an addendum to that, we can actually implement, there may be a way to run actually quantum simulation in a similar way to the quantum simulation experiments on this platform, but to get both XX and YY at the same time.
Right.
Owing to pulse shaping. So there may be some interesting directions with pulse shaping to extend the quantum simulation ability. One thing to note, though, is that the usual quantum simulation experiments are plagued less by this axial motion issue because their XX is done via global beams. So the ions can move as much as they want, the easing stays happy. Where people have done individual addressing was to implement disorder. So your disorder gets more short-term correlated disordered. But I guess that's not as bad as your easing getting smeared out.
Disorder is good. You can do this time crystals or this many-body localization type of experiments, and some of them have been done. Yes, so.
Whereas for us, the easing would get smeared out as well.
Right.
Due to this effect.
Right.
So, so they're very complementary platforms in what they can do.
Right.
So depending if you have one or the other is better targeted. Sorry.
Yep. I'm just checking if there is other questions from the audience. If not, we can take it.
I have one.
Please go ahead. State your name, affiliation, and please go ahead.
I'm Noel at CQT.
Okay. Which group?
From Mukherjee group. Manas
Mukherjee group. Okay, yes. Experimental ion group. Okay, please go ahead.
So you mentioned early on in the talk that you measured the D2 time for the ions to be on the order of a few minutes. I was wondering if you had just by chance done any measurements on the D2 time for the motional modes of the ions.
Yes, we have done this. Is about 5 milliseconds, I seem to remember, for these high order radial modes. We are planning, it's between 5 and 20 milliseconds. We are going to be looking more closely into this soon and see if we can further improve it. The motional coherence times of in excess of 10 milliseconds have been obtained by our Jung-Sang Kim's group with a similar platform.
Okay.
And maybe we can follow their tracks there.
Okay. Any other questions?
Okay, maybe a few technical questions, as Dmitry Matsukevich.
Okay.
So just to understand a little better. So what is your axial mode frequency, the one that gives you so many troubles?
Yeah, thank you. With 15 ions, it is 200 kilohertz. It is, of course, set by the ion spacing, currently 4.43 microns. We can probably decrease that to 3.9 microns with some intervention in the setup with a corresponding increase in the axial. For 25 ions and 4.43 microns, it is about 140 kilohertz.
I see. And what is the heating rate for those modes?
The heating rate is consistent with 1/f power spectrum of electric field. where the heating rate at 3 megahertz is about 100 quanta per second, 80 quanta per second actually, which is consistent with people's experience with EHRA.
Okay, so it's like few hundred quanta per second at 200 kilohertz, right?
No, it goes like the square.
Ah, okay.
Yes.
Oh, then
So,
very bad.
Yeah.
Okay.
It's big.
I see. So, and maybe another question, because it's just kind of probably everybody want to know and everybody are too shy. So how long do your ions live in the trap? Like 15 ions, so
yeah, about between 30 and 45 minutes.
Okay. So after 30 minutes, one ion leaves, right?
Sorry?
So what it means that after 30 minutes, one ion may leave the trap and you have to add one more ion.
No, the losses are always loss of everything but one ion. One ion stays.
Okay.
Good.
And why? Sorry, why is it loss of everything but one?
We believe, as in most traps, that this is a micromotion-driven process. And once you are left with one ion, the micromotion heating stops.
Okay. If there are no more questions, we can thank Marko again virtually, and we can end the session here and continue. Some of you already discussed to do a little bit more chatting following up. So bye-bye. Thank you.
Thanks, everybody.